Okay, in this video, we are going to start Unit 4 for AP Calculus BC, and what I'm going to focus on are two sections in this video. Section 4.1, where we start analyzing functions using derivatives, and Section 4.2, which is kind of an extension of what's in Section 4.1. So we're really shifting gears from Unit 3, when we were essentially just learning all of the derivative rules that we can use in calculus, at least in two-dimensional calculus. So what we're shifting to here is, now that we've learned all of those rules, what can we use them for is essentially what our focus is going to be. And the first thing we're really going to focus on is, how do we look at a function and know what's going on with a function just by looking at its derivative and its second derivative. So some of these things are things that are common sense, that you can kind of look at a function. You can know whether a function is increasing or decreasing. But what we want to be looking at is, how do we mathematically justify that that's what's happening? So in terms of increasing or decreasing, or a function having a constant value, what we're looking for, if it's increasing by a mathematical definition, is if we have 2 points, and I'll show you the diagram here. If we have 2 points, x1 and x2, if the function value at x2 is higher than the function value at x1, then obviously we have a function that is increasing. Okay, the function values are getting bigger. Same thing for decreasing. In that case, the function value at x1 is greater than the function value at x2, then clearly we're decreasing. And then if we have a constant function, obviously the function values are going to be the same over that interval. Okay, so those are kind of the basic ideas in terms of what are we looking at. Now, what we want to do is, we want to really start taking into account what's happening with the derivative when we're increasing or decreasing or constant. So in this first diagram here, we have a function that is increasing in value. And when we have a function that's increasing in value, notice the tangent slopes here are all positive. So what that tells me is that my first derivative is positive on this interval. So if the first derivative is positive, then we know we're increasing. So all I'm doing is showing you the diagrams here that represent each one of these. And so you can see this first one, if the derivative is positive on some interval, then the function is increasing on that interval. And then we can do the same thing for decreasing and for constant. So here you can see we have negative slopes, and all of the slopes are negative on that interval, so that function would be decreasing. So if f prime is less than 0, I know I'm decreasing. And then here we have constant slopes. Obviously then the slope, or the derivative, would be 0, so that tells me my function is constant. Okay, so let's take a look at how can we use derivatives to do this. Well, we've got y is equal to 2x squared minus 8x plus 9. Now, the nice thing about these methods we're going to use is that we don't even have to know what the graph of the function looks like to be able to analyze a function. So even when we get into really complex functions that are very difficult to graph and very difficult to work with numerically, we can still figure out everything we need to know about the behavior of the function just by looking at a derivative and a second derivative. So here what we're going to do is, we're not even going to look at the graph of this function. What we're going to do is analyze the derivative. So y prime, or the derivative of this function, would be 4x minus 8. And when we go through this process and we look for increasing or decreasing, we're going to look for what are called critical points. And critical points are going to be the points where the derivative is 0 or undefined. So clearly this derivative is never undefined, but I'm going to check where is it equal to 0. And in this case, that happens at x is 2. Now, to analyze our function, we're going to use something called a sign chart. And a lot of you have seen these before, some of you may not have, so I'll kind of explain how these work. In a sign chart, basically what it is a number line. But in our sign chart, when we're analyzing derivatives, we're going to look at critical points. So this is just a number line. The only point that's really important for me is the point where x is 2. And I'm always going to label my sign charts, because a lot of times we're going to have more than one sign chart on a question. I want to make it really clear what this sign chart is representing. So now all I'm going to do is test points and figure out, is my derivative positive or negative on the interval that I have here. So I'm thinking about to the left of 2 on the number line, and an easy number to analyze would be x is equal to 0. And remember, we're looking at this derivative. So if I plug x equals 0 into that derivative, I'm going to get a negative value. If I plug a number greater than 2, like let's say I plug 3 in, I'm going to get a positive value. And just from that sign chart, I can tell where the function is going to be increasing and where it's going to be decreasing. So clearly here, the function is increasing when the derivative is positive. So that's going to be increasing on the interval from 2 to infinity, and it's going to be decreasing on the interval from negative infinity to 2. Okay, so it's very easy to analyze these, especially for a polynomial function where everything works out really nicely in a lot of cases and you get very simple roots to work with. Okay, so the one thing I do want to tell you is when you have to justify your solutions for problems like this, a sign chart is a really nice visual tool that we use to represent what's going on with the function, but that does not serve as justification for our solution. So if I were going to justify why is this function increasing, I would say the function is increasing from 2 to infinity because the derivative is positive on that interval, or because y prime is positive on that interval. I would say that the function is decreasing from negative infinity to 2 because y prime is negative on that interval. So it's fairly easy to justify, but the big thing is the sign chart is not your justification. It's just a tool for us. Another thing you can do with these sign charts, when you first look at them, if you're not quite sure what's going on with your function, you can just use little segments to represent the different parts of your function. So for example, here I can see that my derivative was negative, so that means my function was decreasing, and then my derivative became positive. So my function was going down, and then it went back up. And think about a quadratic function with a positive leading coefficient. I know that's a parabola opening up. So clearly what I drew here isn't a parabola, but it does have the behavior of going down and then going back up, just like you would see with a parabola. Okay, so big thing, when we find critical points, we're always looking for the points where the derivative is 0 or where it's undefined. Okay, so let's talk about concavity and points of inflection. So when we talk about concavity, what we're sort of thinking about is, you kind of think about, is it have the shape kind of like a parabola opening up or a parabola opening down. And if you notice here, when we're concave up, look at the slopes in this graph. And if you look at the slopes in this graph, you can see how it started really steep in the negative direction, and they're slowly kind of flattening out to 0, and then they start increasing and getting steeper and steeper. So what we're seeing there are increasing slopes. So remember, the second derivative would be the rate of change of the first derivative. So if I see increasing slopes, that would indicate that y double prime, the second derivative, would have to be positive, because that tells me my derivative is increasing in value. Same thing with concave down. You can see that we started with a positive slope, and then we're slowly becoming closer to 0, so we're decreasing, and then it becomes more and more negative. So the slope continues to decrease. Okay, so in general, if our second derivative is greater than 0 on an interval, we're going to be concave up. If the second derivative is less than 0 on an interval, we're going to be concave down. So it's pretty easy to analyze again. So here's another function. We've got a cubic function here. And what I'm going to do is I'm going to take the derivative. We're looking for, where is this function concave up or concave down? Okay, so my derivative would be 3x squared minus 12. Now, they didn't ask us anything about where's the function increasing or decreasing. If they did, we would use the first derivative. Since they're asking for information about concavity here, I'm going to jump to my second derivative. So my second derivative would be 6x. And now, just like I did with the first derivative, I want to know where's the second derivative, 0 or undefined. We don't really call these critical points, but what I usually refer to them as is possible points of inflection. So set that equal to 0, and I get x is equal to 0. So x equals 0 is a possible inflection point. And in fact, I can actually tell that it is, and I'll show you a shortcut for doing these sign charts in a few minutes. So similar to what we did with the first derivative, I'm going to create a sign chart. This one's going to represent f double prime. And now it's pretty clear. Remember, we're looking at this second derivative. If I plug in a negative number, obviously I'm going to get a negative value. If I plug in a positive number, I'm going to get a positive value. So in terms of concavity, I would be concave down from negative infinity to 0. And I would be concave up from 0 to infinity. Okay, so pretty simple to do. I'm also showing you some really simple examples right now. Sometimes your derivatives are going to get a little messier, and you're going to have a little bit more work algebraically to do to get those critical points, but the main idea is always going to be the same. Okay, so another thing we need to talk about is what's called an inflection point. And an inflection point is just where the concavity changes. So switching from concave up to concave down, or concave up, concave down, concave up to concave down. Okay, so you can see on these two graphs, this is essentially what we're looking at as an inflection point. Okay, so how we identify that is, does the second derivative change sign? And the question here says, for the previous example, where's the point of inflection? Well, take a look at our sign chart here. And in our sign chart, you can see that we went from concave down and we switched to concave up. So for us, our point of inflection would be at the point where x is 0. So we can, depending on how they ask the question, maybe we just need to say the x coordinate. X equals 0 would be where we have an inflection point, or I could give the actual coordinate. And again, it just depends on what we're looking for. This one, it doesn't make it very clear, so I would probably just give the entire coordinate to be safe. So where's the point of inflection? It's at the point 0, -5 on our graph. And you can graph this function on your calculator, this cubic function on your calculator if you want, and you can verify those solutions that we found. Okay, so let's just analyze a few functions here just for some practice. So a lot of this is just going to be you working through some of these problems. I'm going to go through the first one just to show you the work that I would expect to see on a problem like these, and then I'll have you try the second two. So here we've got a quartic function, and what they're asking us to do is determine where the function is increasing or decreasing, where it's concave up or concave down, and x coordinates for points of inflection. Okay, so we're going to need to look at the first derivative and the second derivative. So f prime here would be 4x cubed minus 36x squared. Okay, I want to set that equal to 0 because I'm looking for critical points. And when I do that, what I'm going to get here is 4x squared times x minus 9 is equal to 0. Okay, so clearly I've got critical points at 0 and at 9. Okay, so now when I do my sign chart, remember I told you about testing points. Well, I really don't have to test more than one interval whenever I do a sign chart, if you remember what you learned in Algebra 2 about multiplicity of solutions. So when we talked about multiplicity, when we were finding roots for a function, what you looked at was if you have an odd number multiplicity, that means your graph is crossing the axis at that point. If you have an even multiplicity, that means you're bouncing off the axis at that point. So you can see that at x is equal to 0, we actually have a double root. So I know the sign's not going to change at x is equal to 0, and I'm going to use that as a shortcut. So all I need to do is test one point. And I'm just going to look at these intervals and say, okay, what's an easy interval to test? Between 0 and 9 seems very easy because I could just plug 1 into my function. And where I'm going to test my derivative is in this factored form because that's going to be the easiest one for me to look at. So when I plug 1 in, obviously I've got a positive for 4x squared and I've got a negative for x minus 9. So I'm going to end up with a negative value in that interval. And now using my multiplicity, I can finish out this sign chart. There's not going to be a sign change at 0 because we had a double root. And there will be a sign change at 9 because we had a multiplicity of 1 there. So again, odd multiplicity means there's going to be a sign change. Okay, so from this, I already have the information that I need for increasing and decreasing. I'm going to put all the answers off to the right here, so I'm going to continue on and now analyze my second derivative. So second derivative would be 12x squared minus 72x. Okay, so again, these are not critical points, but we're looking for possible points of inflection. So I'm going to factor this. 12x factors out, and I have x minus 6. And you can see I get x equals 0 and 6. Now, I can already tell that I have 2 inflection points. And the reason I know I have 2 inflection points is because both of these had a multiplicity of 1. But again, on your sign chart, we can show what's happening here. And I'm going to do the same thing I did before. I'm going to use the factored form of my second derivative because it's easier to test. And again, I'm just going to choose something easy to test. So I'm going to choose the middle interval because I can use 1 again. So if I plug 1 in, I'm going to have a positive times a negative when I analyze these two expressions. I don't really care what the number is. I just care if it's positive or negative. And I can see in this interval, I'm going to be negative. And now since each of these zeros for the second derivative had a multiplicity of 1, I know I'm going to see a sign change at both of them. Okay, so from that, now I can answer all of these questions. So the whole thing about increasing, decreasing, all of that information that they wanted me to find, I can now answer that. So this is going to be increasing on my interval from 9 to infinity. It's going to be decreasing on the interval from negative infinity to 9. And all I'm really doing is just reading this information off of my sign chart. Concave up. Okay, you can see we have two intervals for that. We've got negative infinity to 0. And we've also got, let's see, the other interval that we've got is 6 to infinity. So that would be my other one, 6 to infinity. Then we can do the same thing with concave down. Okay, so for concave down, I'm looking where's that second derivative negative. That would be 0 to 6. And then the last part, points of inflection. So points of inflection, you don't really have to write that out. You don't have to write out point of inflection. We usually just use the acronym PI for points of inflection. And clearly we had two here, x equals 0 and x equals 6. And remember, we didn't have to give the coordinate for the points of inflection there because they specifically said the x coordinates for the points of inflection. So always check that because sometimes you need the actual coordinate. If it's a free response question, I'll be kind of picky about that because I want you to be paying close attention to what are they actually asking you to find. Okay, so there's two more problems here. And the first one's a little more complicated because of the derivatives. And the second one's pretty easy, but I'm wanting you to go through it for a specific reason. So take a couple of minutes, pause the video, work through these next two questions. Same thing, find where is it increasing, decreasing, where is it concave up, concave down, and find points of inflection if there are any. So pause the video, and when you come back, I'll show you the solutions. Okay, and here's what you should have ended up with on that one. So what we've got here is the second problem, y equals e to the negative x squared. I didn't show all of the algebraic steps for the derivative. And again, I'm not typically going to get into all of the algebra on these types of problems, especially with the derivative and simplifying the derivative. That's stuff you should know how to do now. So I found my y prime. I would set that equal to 0. There's only one critical point at x is equal to 0. And then for the second derivative, what you're going to find is you've actually got two possible points of inflection, and they both have a multiplicity of 1. So when you do your sign chart, you're going to find that you have actually 2 points where your concavity is going to change. So you can see my intervals. I didn't show my sign charts, but you get the idea in terms of where they come from. It worked just like the last one. I could have shown the sign charts, and I could read the same information off of there. Okay, and then for C, we have y is equal to x to the 4th. And this is actually a pretty simple function. The reason that I wanted to go through this one is because of the second derivative. So first of all, the first derivative is 4x cubed. You can see we have one critical point. You can see that we have one point where the behavior of the function changes from decreasing to increasing. Pretty simple. But on the second derivative is 12x squared. When you solve that, that's a double root. So I'm not expecting concavity to change at a double root. And in fact, it does not, because if you think about your sign chart, it's going to be positive to the left of 0, and it's positive to the right of 0. So on this graph, you can see that this graph is actually concave up everywhere. And the reason that I wanted to point this out is because the number one most common mistake that people make, no matter how many times I say this, is when you're finding points of inflection, don't assume that every point where the second derivative is 0 is going to be a point of inflection. You have to look at that multiplicity, or if you're not comfortable with the multiplicity, you have to actually create the sign chart and actually analyze that sign chart. So take that into account whenever you're looking at the second derivative. Make sure you're paying close attention to that multiplicity. And that really applies for the first derivative as well. But it really tends to be something that people mess up when they're dealing with the second derivative. Okay, so I want to go back to one thing on the first example I went through because I didn't want to throw too much at you at once. But on my sign chart for my first derivative, we had this happen where we had a double root on the first derivative. So when you have a double root on your first derivative and you don't see a sign change, what that means is if you think about what my graph looked like here, my graph was decreasing, it hit a slope of 0, and then it decreased again. So my graph would look something like this, hit a 0 slope, and then go down again. That is what we refer to as a shelf point. So a shelf point is a point where the slope hits 0, but we don't actually have a change in the behavior of the function from increasing to decreasing or decreasing to increasing. So on a shelf point, the reason it's called the shelf point is because you essentially have this kind of flat point in your graph. I just drew kind of a horizontal line through there so you can see that it gets pretty flat. And so essentially you have like a flat area on your graph, which we refer to as a shelf. So that's just a kind of a special case whenever you see the same behavior we were talking about with the second derivative where we don't see a point of inflection, kind of the same thing on a first derivative, except we have a special name for it, which is a shelf point. And the other thing is when you have a shelf point, that's typically going to be a point of inflection as well. And you can see the way that I've drawn this shelf point, you can kind of see how that's a point of inflection because we were concave up, we hit that 0 slope, and then we became concave down. Okay, so let's move on here. And the next thing that I want to show you is continuing the analysis of functions. And what we're going to talk about here are extreme values of functions. So we're primarily going to focus on what we call relative or local extrema. And when I say relative or local extrema, those are interchangeable terms. Some places you look, they're going to refer to them as a local max or a local min or a local maximum or a local minimum. Some places will say relative maximum, relative minimum. They both mean the exact same thing. So I've got this diagram here that's going to show you all the types of extreme points that we're going to deal with. And you can see that obviously a maximum, this is kind of common sense, a maximum is going to be a high point, a minimum is going to be a low point. But we have different types of maximums and different types of minimums. So a local maximum just means that if I look at the points in one region of the graph, I'm hitting a high point. So I can see that my graph goes up and back down. So that's a local maximum. The absolute maximum means it's the highest point on my entire interval. We're not going to analyze a lot with absolute max and absolute min today, but that is something that you need to be able to distinguish between the local max and the absolute max. Same thing with the local minimum. You can see that this is a low point, but it's not the lowest point. And then we've got an absolute minimum here. We have a local minimum at that endpoint. Okay, so that's the vocabulary that we're going to be looking at. And we're going to use a lot of the same techniques we were using in 4.1. And now we're just going to go a little bit further with what we were doing to analyze the function and extend that out to now find maximum and minimum values. Okay, so the first thing we're going to look at is called the first derivative test. And the first derivative test is the most basic max-min test that we have. And it's very, very easy to do because it's common sense. If my graph goes from increasing to decreasing, I have a maximum. If my graph goes from decreasing to increasing, I have a minimum. And then if I don't see a sign change, then there's not going to be a max or a min. Okay, so let's take a look at this one. It says use the first derivative test to find the local extrema of the function x to the fourth minus 12x cubed plus 5. Now, this is a problem that we looked at back in 4.1. So I'm going to skip some of the steps here. What we had was f prime is equal to 4x cubed minus 36x squared is equal to 0. And what we found was that the points we were looking at was x is 0 and 9. X equals 0 was that double root. So here's 0. Oops. Here is 0 and 9. And we had minus, minus, plus in this sign chart. Okay, so that's the exact same problem that we looked at back in 4.1. And now we're going to extend that out and say, okay, now that we have done all of this stuff about increasing and decreasing, how do we figure out where there's a maximum or a minimum point? And it's not really difficult to do because we're going to use that first derivative test. Well, from the sign chart, really, you can kind of reason through with the sign chart. Think about what happens here. This function is decreasing and then decreases a little bit more, and then it starts increasing. So at x is equal to 9, I'm going to have a local minimum because my function went down and then it went back up. So in this case, I would say there is a local minimum, and it would be at the point where x is 9, and it turns out the y value here is a pretty big number. It's negative 2,182. Okay, so there's a local minimum at that point, or you could say f of 9 is equal to negative 2,182. But that's all it is with the first derivative test. It's just an extension of what we were doing with increasing, decreasing. So the one thing I do want to warn you about is if I ask you to justify why is there a local max or a local min, again, like I said before, this sign chart is not justification. That sign chart is just a tool for us to sort of organize our thoughts. So if I needed to justify why is this a minimum, I would say there is a local minimum at f of 9 equals negative 2,182 because the function went from decreasing to increasing at x is equal to 9. So that's all you have to say, and that's what my sign chart is showing. But what I'm asking you to do is explain what the sign chart actually says. So keep that in mind. You've got to actually explain that in words. It's just a brief statement, but you actually have to write out the statement that explains that. Okay, so what I want you to do is try the same thing on this next one. Use the first derivative test to find the x-coordinates of the local extrema given this derivative. Now, the derivative is already there, so you don't even know what the function is, but you do know the derivative. So take a second and analyze that and figure out max min points from that. Okay, and here's what you should have ended up with. And I didn't find the y value this time just because it's a little messy and we didn't have the original function, so we haven't really talked about antiderivatives yet. But I knew there was a double root at 0, and I also knew that at x is equal to essentially the cube root of 5, I knew I had another critical point. So I've got two critical points. One of them has an odd multiplicity, one of them has an even multiplicity. And so here's my sign chart, and it goes minus, minus, plus. So clearly at x is equal to 0, I would have a shelf point. And over here at x is equal to the cube root of 5, I can see I'm going down and then back up. That's going to be a local minimum. Okay, so pretty easy to analyze these once you understand what you're looking at. And if you have the original function and you don't feel really, really comfortable with this at first, just graph the original function after you have your solution and make sure it's matching up with the behavior that you're predicting using the derivatives. All right, so let's move on to look at another type of test. So this is called the second derivative test. The second derivative test is another way that we can find maximum or minimum values. And the way this test works is we're essentially going to determine whether we have a max or a min based on the shape of the graph. So we're going to combine two pieces of information on this. We're going to look for the points where our derivative is 0, and then we're going to look at those 0 points, those derivative 0 points. Is the graph concave up or concave down? So you can see on this diagram that I have here, if I have a maximum, which is this point right here, if I have a maximum, I have a 0 slope, and then my graph is opening down. I have concavity, a negative concavity. Okay, if I have a minimum, like you can see on this point, I've got a 0 slope, but my graph is concave up. Okay, so it's pretty easy to analyze. Sometimes we use this test because we have limited information about our function. And if the only thing we know about our function is what's happening at certain points, we can still identify max and min values by combining information about the derivative being 0 and the concavity at that point. Okay, so here's the same problem that we just looked at. So same exact problem that I showed you a minute ago, x to the fourth minus 12x cubed plus 5. So we've seen this problem a few times now. So I'm going to just verify the local extreme values that I found previously using the first derivative test. So we already know that f prime is equal to 4x cubed minus 36x squared. We're going to set that equal to 0, and we get x is 0 and 9. We don't need a sign chart for the first derivative. There's no sign charts in the second derivative test. Now I'm going to look at my second derivative. It would be 12x squared minus 72x. I'm not going to set that equal to 0. What I need to know is, what's the second derivative at 0? Well, at 0, the second derivative is actually equal to 0, which we kind of should have expected. If you remember, at 0, we had a double root, and that was a point where our graph changed concavity, but it wasn't a point where it was a max or a min. So again, I kind of drew what that shelf point looked like earlier and kind of think about that. It's not a maximum or a minimum point, and this is just verifying that because I don't have concavity at that point. If I found the second derivative at 9, I get 324. So that's a positive value. So that's greater than 0. So now in terms of the second derivative test, I'm going to show you how I would write out my justification. So I would say f prime of 0, or excuse me, f prime at 9 is equal to 0, and f double prime at 9 is greater than 0, or you can put the value, it doesn't really matter. So in this case, there's a local min or a relative min. And you can write out minimum if you want. I usually just abbreviate. And there's a local min at f of 9 is equal to negative 2,182. Okay, so I just wanted to show you the justification. And if they asked about what's happening at 0, I would say there's no max or minimum at x is equal to 0, not because of the second derivative test, but because there's a double root at 0. But from a second derivative test standpoint, when I see something like this, that means my second derivative test is not giving me information about what's happening at 0. So remember, the second derivative test only is going to give you information if your second derivative is positive or negative. And that's what we had here. These first two are the ones where we can come to a conclusion. The last one here, when the second derivative is 0, then we know that that test is inconclusive. All right, so let's just take a look at one last thing here. We're going to talk about curve sketching. And this is kind of complicated, so I want to warn you in advance. You might struggle with this a little bit at first. It's something where it takes a little bit of time to get used to piecing all of this information together. And that is something that you're just going to have to practice with a little bit. So I'm going to show you one of these, but you're going to have several of these on your homework. Okay, so what we're given here is the derivative. And what it says is to sketch a possible graph of the function that goes through the origin. Okay, so what we're going to do is use the information like we've been looking at for the behavior of our function and for extreme points. We're going to use the same type of information, but we're going to piece it together to create a graph. So I've got 4x cubed minus 12x squared. I'm going to set that equal to 0 because that's my first derivative. And I would get x is equal to, well, let's actually show the factored form. 4x squared times x minus 3. I would get x is 0 and 3. And I wanted to show the factored form just to make it really clear that I had a double root. So 0, 3, this is my f prime. And now just test a single point. I'm going to plug 1 into the factored form of the derivative, and I can see that I get a negative value. Since I have a double root at 0, the sign's not going to change. An odd multiplicity root at 3, the sign will change. Okay, so that's part of what I'm going to use for my graph. Now, in addition to that, I want my second derivative. F double prime would be 12x squared minus 24x. And I'm going to set that equal to 0 now. So again, factor this, 12x times x minus 2 equals 0. And I can see x equals 0 and 2. Those both have odd multiplicities, so I'm going to see sign changes on my sign chart for the second derivative. And now when I go through here, I can see that if I'm less than 0, I'm concave up. In between 0 and 2, I'm concave down. And then greater than 2, I'm concave up. Okay, so all of that information now we're going to piece together to create this graph. Now, this graph really could be located anywhere unless we're given what's called an anchor point. And see how they told us here that this has to go through the origin? That's forcing our function through a certain point, which that point is going to anchor this graph into a certain position. If we didn't have any information about what point this graph has to go through, then we could put this graph anywhere because we don't know what the original function is. So I don't have any way that I can put this in place. So since I do have that point, that's what I'm going to start with. And now what I need to do is sort of break this into pieces. And I'm going to use both of my sign charts at the same time to create this graph. To the left of 0, you can see that my function was decreasing and concave up. So decreasing and concave up, that means that to the left of 0, my graph's going to look something like that. Okay, so now the other points that are going to be important are going to be out where x is 2 and where x is 3. Okay, so let's look at the points between 0 and 2. Between 0 and 2, you can see I'm decreasing and I'm concave down. At 2, I'm going to hit an inflection point, so I have to remember that. Okay, so from 0 to 2, I should be decreasing and concave down. Okay, so now between 2 and 3, now my graph is concave up, and it should still be decreasing. Now notice at 3, I had a minimum point. That's going to be a slope or a point where the slope is 0. So I know I'm going to come to a 0 slope point here. And then the last section of my graph, you can see it's increasing and concave up. So it's going to continue on like this. Okay, so that's kind of a rough sketch of what that function would look like. Now, I don't know exactly how far up or down this point went. It may go down much more than that. I didn't really get into that level of detail. What I'm looking for when I sketch these is just a rough estimate of what the shape would be. And then if I'm given specific points, I can anchor that graph into a certain position. Okay, so when you look at that, it's pretty easy to kind of get a gauge for whether or not this is correct because we have a polynomial function. And you can see that we're given the function 4x cubed minus 12x squared as the derivative. That means the original function would have been a quartic function. And you can see my graph that I've estimated for the original function is a 4th degree function. Okay, so down below here, what we've got are some kind of typical shapes that you would see in the different situations that you might encounter. So derivative being positive, derivative being negative, concave up or concave down. So what you have to do is kind of piece things together. You start to get a feel for if a graph is increasing and concave down, what does it look like? Decreasing and concave up, all of those things that you have to piece together section by section. You'll have to think through that a little bit at first, but you'll become more and more comfortable with it the more you graph. Now, when you do the homework, there are a few questions in Wiley Plus where they're going to have you sketch graphs. And they have a tool in there that allows you to kind of sketch what things look like. So do the best you can with that, but I would say also try to graph it on your own. Just graph it on your paper. Last thing on this set of notes is a problem where we're going to go through doing some things on the calculator. And I'm actually going to show you this one in class because I want to go through a lot of the detail on what to do with the calculator for this. So you can try that one on your own if you want, but we will go through that during synchronous time.